Welcome to the Andreas Orthey podcast series on robotics. My guest in this episode is Sean Murray. Sean is co-founder and director of robotics engineering at Realtime Robotics, a company specialized on generating collision-free motions for industrial robots. In this episode, we will talk about his past as a chemical engineer, how to be effective in the robotics industry, what the biggest challenges are for robot manufacturing, and the future of real-time robotics. I'm happy that he was able to join me. Please welcome Sean Murray. Hello, Sean. Thanks for doing the podcast. Thanks for coming to Berlin.
Of course.
So you are currently located in Montana, right? Mm-hmm. But today you're here in Berlin, Germany.
Yep.
So what made you actually come around this time?
Yeah, so sometimes it feels kind of surreal that we have an office in Berlin, because it seems like, just yesterday there was three of us in a different co-working space in Boston. So yeah, here in Berlin for a few days on my way to visit some partners in Finland, and decided it made sense to stop by and visit our awesome team here.
Cool, that sounds good. So let me start a little bit with your background. So can you maybe tell me a little bit about the place you were born and how it maybe shaped your upbringing?
Sure. So I was born in Texas, but moved around across the states, growing up. I don't know how much it shaped my thinking, except for like being open to kind of whatever happened, So when I was in grad school and, things happened and we thought about starting a company, I was like, all right, let's do it. Let's see what happens.
That sounds good. And so when you were still in school, so what kind of topics did you really enjoy and what kind of topics were you really good at?
So, I was always really interested in, computer stuff, when I was, early teen, my dad gave me one of those like programmable, calculator type things. And I really enjoyed like learning how to program that. And then programming computers, and so really enjoyed that. Enjoyed math stuff, pretty much anything science related. I really enjoyed.
So what was actually your first contact with a computer, or maybe like the first program you wrote also?
Some kind of game, I'm sure. Like most kids, you like games. As soon as you like playing games, then you want to make your own games, and so something like that.
And did you already know that you wanted to do something with programming at that time, or what was your vision for your life when you were still growing up?
I don't think I really had a vision. I wasn't the kind of kid. My brother, for example, knew he was really into like space from a young kid. He was super into space stuff. Mm-hmm. He wanted to be an astronaut. I wasn't really like that. I was just kind of like, I was along for the ride.
And so is your brother actually doing something in space?
No.
Okay. But before you actually went to the whole computer science path, you first actually stopped and doing some chemical engineering, right?
Yeah.
So can you maybe tell me what motivated you to pursue a degree in chemical engineering?
Yeah, I originally wanted to go into like biotechnology. Mm-hmm. There was I was going to school in like 2007 to 2011, and so there was a lot of exciting stuff going on there. So that was my goal it was a pretty tough time in the job market. So I ended up doing more like stuff like for the energy industry, doing reservoir simulation type stuff. Mm-hmm. Did it for a few years, really enjoyed it, but at some point decided I wanted to try something new, and went back to school and decided to study computer architecture.
But if you had like a background in like programming, how did you actually think about like going into like, for example, computer in chemical engineering? So I think that is like a big jump, right? So how did this actually happen? Did you want to like program live or something?
No, I think I was just really interested in biosciences at the time. There was a lot of computing going on, and still is with bioinformatics, like kind of analyzing, genetic data, and was intrigued by that. Mm-hmm. And at Rice University, they had a really kind of strong collaboration between their chemical engineering and bioengineering departments. So that seemed like a cool place to be.
Mm-hmm. And so what kind of thesis did you write about chemical engineering in science?
We actually didn't. I'm trying to think. I don't think we really did theses in our undergrad.
Or maybe some project.
Yes. So there was a. I'm trying to think of any that really stand out, but we did fun classes in kind of like modeling the dynamics of different genes and species over time. We did we had some classes in like protein engineering. I'm struggling to remember any of those projects, so long ago now. But yeah, fun ones.
But something which seems to be really interesting is what you already mentioned, like reservoir engineering. Can you maybe tell me a little bit, or can you maybe describe what reservoir engineering actually entails to someone maybe outside the field, and what excited you most about it?
Sure. So reservoir engineering is kind of the science of how to best manage a system that can be kind of modeled as a closed system. It has temperatures and pressures and different fluids in it. And as you take, you're not just taking things out, you're also putting things in. So usually what you do is you model the system, you discretize the system, like most modeling, you discretize the system somehow. You apply the natural laws that govern it, so fluid dynamics, pressure gradients, temperature gradients. You model and see, okay, if we drill these holes in these locations, it's going to drop the pressure in these ways. Some gases are going to come out of solution, which may or may not be desirable. You have rocks with different porosities, and so you're also taking measurements. And so you might have a reservoir that's 300 feet thick, but the 300 feet is not homogeneous. It might vary from almost no porosity and no permeability to very porous and very permeable. And so you use the data you have to create models, which are always imperfect, and then you try to predict what will happen if you do different things. And so you might be anticipating, or you might have a goal to get out 80% of fossil fuels in a reservoir, and you can kind of test different strategies and simulate how that might how different development strategies might work or might not work.
And so what is the biggest challenge there? So what would actually happen to the reservoir in the worst case if you do something wrong?
So there's a lot of challenges. This is a whole field. There's entire certain schools of whole programs on this. But so just as an example, so you'll often this is going to be a huge tangent, but that's okay. So the way that most of these things usually start is you might start with seismic data. You haven't drilled anything. You've just taken measurements from the surface, and so from that you have a very, very coarse model. It's not going to be very accurate, but it's going to have been pretty cheap to get that data. Then you might drill a test well, and so you drill the hole and you log. It's called logging the hole. So you stick sensors down the hole, and you take measurements, and you see what's in there, what kind of rock is in there, what kind of fluid is in there, and that gives you one data point. And so you might try to extrapolate. You combine that with this other data, and so one thing that might happen if you didn't plan well is the more you decrease the pressure in these reservoirs, the more you might have things come out of solution. So in kind of very old school, let's take it before reservoir simulation was a thing, back when people were just drilling and pumping, all they were doing is you'd only get about 15, call it maybe max 30% of the actual fossil fuels out of reservoir, and then that would be it. Which is obviously pretty inefficient and kind of wasteful.
And what happens with the rest of it?
You can't really
reach it anymore.
So there's a few things that'll happen. So one is if you're just trying to pump stuff out, you reach a point at which the pressure has dropped so much that that gas is separated from liquid oil, and the pumps are usually designed to move liquids and not designed to move gases, and that technology just doesn't really work very well. And so as the industry advanced, different techniques came into where you start pumping water into the reservoir to keep the pressure up, and also push fluids around, which works. And you can also do things like mix surfactants into the reservoir.
So what are surfactants?
Surfactants are chemicals that kind of, you can think of them like soaps, basically. Like, obviously if you've tried to clean, oil with water, it doesn't work very well. You use some kind of something to break the surface tension, and you can also, pump carbon dioxide down in there, which is a great solvent and makes oil more mobile. I feel like I'm getting into a whole different topic here.
Yeah,
I don't know.
that's true.
I don't know how these boats going to be.
So maybe let's wrap this topic up.
Sure.
So what would you say were maybe like some bigger lessons which you learned from your time there?
I think
which you can maybe still apply today.
Yeah, I mean, it was just to me, it was an interesting industry. It had a lot of inertia behind it. It had a lot of science behind it. It had a lot of R&D behind it. And it also used computation in an interesting way. Like that was kind of what appealed to me about it, is that it, you would take this kind of big system that was kind of opaque, and you would use certain measurements and build up a model of how it behaved, and try and use that model to predict how different strategies might work out in the long run.
Okay, and then after 3 years as being a reservoir engineer, roughly, you actually made a very drastic change and you started a PhD in computer science. So was there maybe a moment where you realized that you wanted to go down this road and not the road which you are currently on?
Yeah, I think I was just, realized I didn't want to do that for the rest of my life. It was interesting, but nothing is interesting forever. At some point you want to try something new. I was at an age where grad school still made sense, and yeah, I was excited about computing, where it was going, and yeah.
And what kind of options did you consider before committing to do a PhD?
I considered a few. I was pretty certain I wanted to go back to school. I was considering a few different, topics. I was pretty interested in distributed systems, high performance computing, specialized computer architectures. So I was looking for something in one of those fields.
And then I could imagine that it was pretty challenging to actually get into a PhD program in computer science with your background, right? So how did this actually happen, that you got a PhD position in computer science with a chemical engineering background, and what were like the main challenges to go into?
Yeah, I didn't get into many programs. I think most of them saw my background and weren't really interested. They probably had better options, but luckily Dan Soren at Duke, for a reason, saw something in my resume and interviewed, and decided to give me a chance.
Nice.
And yeah.
And do you think your time as a chemical engineer actually gave you maybe like a unique perspective on problems in computer science, or gave you somehow like an edge compared to like classical computer science students?
I don't think the specific industry gave me an edge, but I think having worked at all, I think definitely gives you perspective that you don't get from just going to school. And so I definitely felt like those of us in grad, because I wasn't the only one who had a little bit of work experience, but I definitely felt like those of us who'd spent some time in industry had a sense for like a little bit more of, you just know a little bit more about how the world works, and any experiences could be helpful in that.
So you would say more down to earth compared to other students?
I mean, down to a little bit of down to earth, but just kind of, when you're 22 and maybe just finished undergrad, there's a lot you haven't experienced in the world, and just having maybe a little bit broader range of like what goes on out there is helpful.
Yeah, I guess so. And so how did your PhD start, and what were your main goals at the beginning?
Yeah, so I was working with Dan Soren so it was actually in computer engineering, which is tied up in their electrical engineering department. And I was interested in computer architecture, which is what Dan works in. And I didn't start with any specific goals. Like I wasn't the kind of student that came in and was like, okay, this is the specific topic I want to dive into. And so I want to say it was only maybe about 6 months into it that we met George Conadaris, who had recently started in the robotics department, or I guess it was the CS department, kind of in a a budding robotics, subfield there, and talked with him, and Dan had kind of been talking about how computer architecture could help, maybe help in some particular computing problems in robotics. And that's when, we started talking about motion planning. And in particular, we started off working on specialized computer architectures for collision detection. So we hadn't even really gotten to the real motion planning parts yet, just collision detection, how to tell if two things are intersecting, really quickly.
And then at some point you published a very influential paper, namely Robot Motion Planning on a Chip, which is your highest cited paper. So can you tell me a little bit about the ideas which maybe came already like from this whole collision checking, and how did they actually mature into this paper?
Yeah. So we were doing really fast collision checking on FPGAs, and we thought it would be cool to kind of do a kind of an end-to-end demonstration of what you could do with this. So we were using the Canova Jayco arms, which was, they were at the time one of the kind of popular ones to use in academic papers, because they were very safe arms. They didn't move super fast. They came with a built-in gripper, so you didn't have to like buy your own gripper. And so we set up I'm trying to remember the demonstration exactly, but so we basically built a roadmap of motions for the arm, and we were using Kinect cameras, which I'm sure you remember, like back in the 2010s were super.
They were a really big thing. Yeah,
exactly. Really big thing in robotics. This video game camera, because you could get, and I think this was the proliferation of those 3D cameras is probably a big reason of why not only us, but like I feel like a lot of other companies kind of became founded around that time, is that these cheap 3D cameras, which hadn't really been available before, like all of a sudden, it went from the Kinects to the RealSenses, and like then after that, like a bunch of 3D cameras became available, and before then there weren't very many options for that. But when you could get 30, 60, or 90 frames per second of fairly decent 3D data, a lot of researchers started to do things with that data. And so back to that first project, I want to say that we had like cardboard boxes, and we would have the robot pick up, I don't know if it was like a ball or like some kind of a toy. And we weren't even like, at that point, I don't think we even really moved him around while the robot was moving. We just kind of like moved it around, and it would like, kind of demonstration was that, you would like hit, I think we put like a big red button to make it really visible, like when we would send the data to the FPGA, and it was, super fast. They would like just do all the collision checking and then find a plan to the roadmap around the boxes, and that was kind of it. It was pretty primitive compared to what we do now, but
So it was basically collision checking on an FPGA plus Kinect sensoring, and everything combined with like standard motion planning algorithms, right? So that was basically how you could describe it, like in very simple terms, right?
Yeah. I don't even know if it was, I wouldn't even, this kind of standard motion planning algorithm, I think it might have been just like a fixed roadmap. I don't even think it was doing any real planning. Honestly, it was pretty primitive, what we were doing.
So it was still primitive, but still it gave you like this idea of maybe there's something bigger behind it, and maybe we can actually go out there and start a company. Can you maybe walk me a bit through this whole process of like conceiving this idea? And when did it actually all made sense? And when did it actually click for you that we should do a company?
It exposed us a little bit to like the problems and challenges that exist in robotics. And then it connected us with people that were interested, who kind of each person we talked to explain like a different aspect of the problem, because one of the things in robotics is it's a very obviously very broad term. Everyone's using these robots for different things, so they have different challenges. And we were trying to identify like commonalities in those challenges. And so one commonality is that robots are really easy to crash into stuff. Anyone who's tried to get a robot to do stuff realizes that if you're not careful, it's gonna crash into stuff. And so our goal was to make it easier to deploy robots and not have to think that. And if you're trying to do robots to do X, Y, or Z, you can focus on X, Y, or Z and not on how to not crash into stuff. And we wanted to kind of make a product that would do that, and we do it very fast. And I think that we probably marinated on the ideas for probably at least a year or so. But we kind of started to get more interest from industrial type companies, and at a certain point, we realized it made sense to give it a go and make a company out of it.
And how did you envision your first product, and maybe which market segment that you wanted to tackle in the beginning?
Yeah. So at the beginning, we were definitely thought that we'd be operating in a very dynamic space with lots of obstacles that were like not predicted. This is around the time when like collaborative robots were becoming more of a thing. The UR robots had come out somewhat recently, and there was this vision that a lot of people had of like having pretty close human robot collaboration, and we had envisioned being in kind of that space. And so our first product was an FPGA board, a PCI, which you would put in on a PCIe slot, and a library to talk to that board. And our thought was that we would be a component in a much more complex system where you would feed it obstacle data, and we kind of had like a standard for how you would communicate obstacle data to this board, and it would tell you back which motions were safe and which motions were not safe. And we very quickly realized that was not what the industry wanted.
And how did you actually find out that this was not what the industry wanted?
Well, by trying. Some of the things you can learn by just talking to people and guessing, but then some things you just try. And so we tried, and we worked with some great partners and sent them, sent them these prototypes and these boards. And what we realized is that that was a pretty low level interface, and most of kind of in real industry, most things are kind of, people want to be kind of plug and play, where they don't want, most integrators, out building robotic work cells, don't want like a C header file in a library to program against. They want something that has like that they can basically plug in, that has some industrial protocol to talk to it, and just go. They weren't really interested in something so low level.
And then how did it actually happen that you found your first customer, and what was the story about that?
I want to say that one of our first touch points with industry was back when we were at Duke. I want to say that Amazon Robotics hosted some kind of like a symposium or something like that, and where just kind of like talk with the different robotics faculty at the university. It might have even been like multiple universities. I can't quite remember, but so we talked with them there, and they we did some early projects with them that were really beneficial in terms of like stuff that we learned.
Nice. And then I guess one of the biggest challenges for any startup founder is, of course, to get funding. So how did you actually acquire funding in the beginning, and who did you consider actually asking for funding?
So I'd say that the best thing we did for getting funding was find a great CEO. So one of the first things we did was we found Peter Howard, who been our CEO since we started, and we looked high and low. I think we were open to all sources of funding at the beginning. I'm trying to remember now. We started when we went full time at Mass Robotics, which is a robotics focused co-working space in Boston, and that connected us with a lot of different industry partners, and some of those became our first funders. Among them, Mitsubishi has been one of our strongest supporters for the longest time, and so they've been involved from very early.
Cool. And what do you think was maybe the biggest challenge which you faced in the beginning of the company, and how did you overcome it?
I mean, looking back, it seems like it was just one. We were taking it, week by week, one challenge after the other.
Yeah.
I mean, there was just a lot of stuff early on. Getting our first. So initially, we had been using off-the-shelf FPGA called development boards. So they're FPGAs combined with a bunch of other stuff that people commonly use for prototyping. But initially, well, we knew that to be kind of commercially viable, we would need to make our own circuit boards. So getting the first, and getting our first custom circuit boards out was probably a big first step. There was a lot of stuff that goes into that.
And what would you say was maybe like the best decision? So I think Realtime is already like almost 10 years old. So what do you think was like the best decision to set up Realtime really for long-term success?
I think the best thing that you can do to set up any company for long-term success is to hire the right people and have the right culture. Because what you realize when you're growing a company is that very quickly the capacity of the organization is going to really outstrip what you as an individual can do. And so it really relies on you hiring great people, kind of, getting them bought into the same mission as you, and growing that. So I think finding the right people is definitely the best decision you can make.
Yeah, that's a good point. So how do we actually find the right qualified people, and what would you say is like your philosophy behind attracting them?
I think that more so than even just qualifications is their passion and their kind of fit in your culture. Because you can if someone has the motivation and passion, you can train them to do pretty much anything. Because and it's going to be more of like, do they have? I think what's a lot harder is figuring out, do they have the motivation and passion that's going to let them kind of continually, especially in a field like robotics, like it changes super fast. We've probably gone through 3 major kind of like shifts in terms of what we've been focusing on just as we learn more. And so like we're working on things that are totally different that, we didn't really expect to be working on. And so it's a question of how do you find the right people? If I had a list of 3 things to do, find the right people,
yeah,
I would definitely give them to you. But I'd say it's a combination of just being open-minded, talking to meeting a lot of people, and yeah, I don't know, I don't have a great answer to that.
Yeah. And a different question also related to this is, of course, how do you keep people? So especially when you have like a startup environment where you have a high risk, and maybe you have also not already like implemented all the structures which other established companies already have. So how do we actually make sure that people are staying?
Yeah, retention is definitely, really key. So I think you definitely have to treat people well. That's a no-brainer. Like if you don't treat people well, they'll find better opportunities. The best people have lots of options, and so you definitely want to treat people well. Make sure that you have reasonable expectations. You provide good feedback, provide good growth opportunities. I think engineers love working on things where they can see the impact. So making sure people get to see the impact of what they're working on. But it's definitely true that as a startup, you oftentimes don't have the resources or the kind of capacity to recruit people as some other like bigger organizations. So you have to make up for that in other ways. Whether that's having a great culture, really interesting problems, the ability to work on things that people want to work on. So yeah, I think you have to kind of use what you can offer, and yeah.
Yeah, and I think there's also a third problem. I mean, even if you get like hiring and retention right, then you're still like in a very highly fluctuating startup environment, right? So how do you actually make sure that, for example, that you keep technical expertise still inside of the company, even if there are like people come and go?
Yeah, I mean, good documentation is crucial. You definitely want to encourage a culture of writing stuff down, so that because obviously, inevitably, people will, even if you're the best employer, people are going to leave at some point, and you don't want that to create an abyss of like a lack of knowledge. So, creating a culture of like, okay, when you create a new feature or a new architecture in the product, like documenting how it works, with the idea that someone should be able to step in and after spending like a half a day or like a day reading through it, being able to understand it. And that's obviously easier said than done. The more fun part is building the stuff, not writing about the stuff. So you definitely have to kind of constantly encourage people to do that.
And so for people who might be interested in working for real time, what do you think are like essential prerequisites, and maybe what kind of topics should they have studied?
Yeah, I mean, I think that if you want to be an engineer at real time, we don't really have a ton of formal requirements. Having some kind of a degree. I think we generally, if you're a new graduate, probably something in a computing type field. I think that one of the things that really separates good engineers and great engineers is the ability to communicate well and the ability to reach out for help when needed. I think that there's nothing quite as frustrating as realizing that like something could have been done 5 times faster if someone had just like reached out with like some basic questions early on and avoided going down the wrong path. And I think that great communication is one of the invaluable skills that you can develop.
So do you think like great communication is like the most critical skill which people need to have to like stand out and deliver real value, or other skills which you think are also as important?
I mean, there are definitely, the kind of basic, engineering skills of knowing how to like break a problem down into sub problems. Those are almost like table stakes, but I think that, some people obviously do them better than others, but I think when I see, things that make certain, individuals able to really kind of magnify the impact of their work and kind of how effective it is, I think communication is definitely a big part of it. The ability to work well with others is something that certain engineers really really thrive on, but other people find challenging for sure.
And so you have already like visited the academic world about motion planning, and now you're in the industrial world of motion planning. What do you think are like the biggest differences between them? And do you think there are some things which people in the academic worlds do wrong, or maybe not wrong, but maybe differently, or maybe not something which produces real value also?
Yeah, the differences are really big, and this is true, most fields. It's not like this is unique to robotics, but like academia is often focused on, pushing the boundaries on what is kind of theoretically possible, and the industry is focused on, things that you can that make economic sense right now, and I think so. I think that what we've learned. The more we've learned about industrial robotics, the more kind of basic it seems in terms of the problems. The problems they're solving are fairly seem kind of mundane when you look at them from an academic sense. They're not so concerned about probabilistic completeness or any kind of like guarantees on an algorithm might provide. They're a lot more focused on, okay, is this going to take me 1 day to set up or 5 days to set up? The fact that you might guarantee that it gets set up after eventually, this is interesting.
Yeah.
And so, in particular, I think what the kind of niche that we're currently, focused on is multi-robot work cells and figuring out how to have multiple robots working really efficiently with each other. So yeah, not even taking like the human kind of throwing all the human collaboration stuff out the window and just focusing on, okay, you have somewhere between 2 and 16 robots in a space that is pretty tight, because space is at a premium in these really big factories. So you're pretty space constrained. You're trying to move around in a very cluttered environment. Lots of machinery, lots of cables, lots of clamps, and you have a lot of literally moving parts. And how do you keep them all collision free? And so it's a pretty different problem than we started on, but I think that's kind of where, at least in the the automotive industry, which is one of our biggest kind of focus areas, is right now is multi-robot programming, which is just really time consuming to do conventionally.
Yeah. So let's talk a little bit more about products. So what would you say is like the product you are most proud of at Realtime, or maybe the product which delivered maybe like the biggest value in the long term?
Yeah, so I'd say that what we're focusing on right now, which we're calling our Resolver, is a tool to do multi-robot programming in an automated fashion. So it's a tool where you upload CAD data for your Workcell, which includes the points of interest that you need the robots to get to. It can include the constraints you might have where certain points might need to be visited before other points. And you get back a really well optimized plan for all the robots, interlock signals that kind of keep all the robots in sync and avoid collisions, and really take this really challenging problem of, okay, how do you because in these work cells, you might not only do you have multiple robots, but you have many points of interest. So in a spot welding cell, you might have each robot that needs to visit 15 points. Multiply that by 15 robots, and you kind of have a lot of different orderings that might work out. So the combinatorics work out so that it would just a human programmer just can't try all of them. We have a product that will explore that state space for you pretty quickly and give you a result that is very, very good.
Can you maybe walk me through, like, so imagine that I'm like a manufacturer, I have like a lot of robots, I want to like, I don't know, assemble something together. So what do I actually need to provide in order to make it work?
Yeah, so at the bare minimum, you need CAD data for your work cell, which luckily most customers building these complicated work cells already have, because they're the people they're using to fabricate the equipment and everything. They need this data. So and this usually comes to us in the form of like a step file or JT files. So you need CAD data for the work cell. You need kinematic descriptions of the robots. So because there's a lot of different robot manufacturers out there. They have different ways they move around. So you need the kinematic descriptions of the robot. You need to be able to tell us where your points of interest are, so where you want the robots to go. And we accept all this data through kind of very common REST APIs. And so if you have an account with us, you can send that to us on the cloud, and we'll crunch the numbers and get back some motion plans for you.
And what do you think are the most important factors which actually shape a successful versus a failure or a failed product?
Well, I guess you have to listening to the customer. So I guess I guess you have to get early feedback, because you'd rather you hear early on if you need to shift the product. But a successful one's going to be one that the customer is satisfied with and gets value from. Not just one that because even if you sell the first two and you make money, but if the customer is not getting value from it, you're not going to sell anything past the first two. And so you want to make sure that the product is bringing value to the customer. So understanding what the pain points are, in the industry, and that was one of the reasons. So why we're focusing on this now is that from our early talks, we ended up talking with different people, and we kind of got guided from our initial thinking of dynamic obstacles, dealing with that. We would pitch this to people, and they'd be like, that's not really something I'm looking for right now, but I have this big problem that it takes me 6 weeks to program this work cell. That's 6 weeks that the factory's not making cars. And if I could turn that 6 weeks into 2 weeks, that would help us out a lot, and so that's kind of how we got to where we are now, is learning about the customer pain points, and then kind of diving in deep and understanding, why is this a painful process? Can we do something to help resolve that? And then as we start to develop a product, getting early feedback on how the product works, if it's doing what the customer expects, because then you'll hear back, oftentimes you'll hear one thing and you'll address that one thing, but then you'll realize that there was like a few other hidden requirements that you didn't know about. And I think that's definitely been a common theme, is that it's quite hard to kind of extract all of the requirements for the product the first go around, because the customer maybe thinks that there's one problem and that problem does exist, but there's also kind of like 4 or 5 related problems that because they had this first problem, they didn't think to bring up those 4 or 5 related problems, but those always come to the surface eventually.
And do you think there are other current challenges in the industry which real-time could maybe address in the future, or maybe even right now?
I mean, there's definitely a lot of challenges in the robotics industry. I think that we'd like to get to, there's a lot of ones that we'd like to get to. I think that we definitely have plans in the long term to get to tackle more of the dynamic, work cells where things are kind of changing every cycle. There's a lot of the big players in the robotics industry, which traditionally have been automotive companies, are fairly slow to adapt. So I think that as they start to use more kind of like cutting edge technology, they'll probably be open to using more, but kind of having them modernize their processes is kind of a slow to happen.
And so do you think that real-time is moving also towards like a long-term goal, or would you say that it makes more sense to actually go product by product and just look out one ahead?
I mean, you want to have a long-term goal, but I think you also have short-term business goals that you need to kind of hit to keep the company going. And so we definitely have much broader ambitions for the long term. I think for the near term, we're really focused on this product and getting wide adoption in the market and continuing to improve it. Like there's still a lot of things we want to do on this product. And yeah.
And so I already mentioned that real-time is almost like 10 years old. So where do you think real-time will be in another 10 years time?
It's a great question. It's hard to say. I think that we have great hopes in our current kind of what we're doing right now. So what we'd love to see is in 10 years that everyone programming multi-robot work cells is doing so with the help of our tool set. I think that we're pretty confident that it's the best thing on the market right now for multi-robot programming. And so we'd love to see that kind of achieving really good market reach, and hopefully at that point we've also kind of really managed to get back into the space of dynamic work cells, kind of more kind of semi-structured work cells where we're seeing a lot more people doing volume, high variability manufacturing, where you might be making a certain part for a couple months and then you want to retool and make a different part. And I think that with our products, you can do that a lot easier.
And do you think that the advent of like AI tools has changed a lot? I don't know, the landscape maybe of problems, or maybe the company itself?
I think there's a lot of companies out there figuring out how to use all the recent advances in it. So I think that where it's affected probably the industries that we're working with the most is in the computer vision space. I think that the advances in computer vision have really enabled a lot of more stuff in logistics, doing kind of dynamic palletization, multi-SKU palletization. Really requires good computer vision, and I think in the past it's probably only been in the past it's hard to say if it's 5 years, 10 years, or 15 years, but fairly recently has the computer vision become available to kind of do that really well. And I think that's where I've seen it the most. I don't think the kind of more recent generative AI stuff has affected our customers as much yet. probably will eventually, but I'm still kind of waiting to see what the big impacts will be there.
So do you think that robotics will be revolutionized by large language models or something similar in robotics, or might be foundational models?
I'm more of a skeptic there. I think that maybe at the layer of communicating intention, so maybe at like the layer which they interface with humans might make advantage of LLMs. But I'd say I'm definitely more of a skeptic on what's going to happen there. So we'll see.
So you don't think that tools like for motion planning, which are already like established, they will not be, I don't know, gone out of business?
I don't think so. I think that I think that they'll prove their usefulness over the long term. Anything can happen, but yeah, I don't think motion planning is going anywhere.
Yeah. Okay, and so yeah, I think that was already like a long journey, like almost 10 years. But is there maybe like some piece of advice would you give your younger self if you could go back in time and say, okay, do this before you actually go and start a startup?
I mean, we definitely, if we with knowledge, with all the knowledge we have now, we would have made very different decisions. I think that usually when we've made changes, we've probably on average made them a few months later than we should have. And so I guess one piece of advice would be don't be afraid to change quickly. It's a balance though, because you want to focus on things and see them through. You also want to be open to feedback, from customers, from the market, from, industry. If you need to, change, that you want to hear that feedback early and change early, rather than wasting time on a route that might not be the right one to go down. So
you would say like pivoting towards like a new idea is also super critical instead of like trying very hard to like push your product through.
Yeah, because I think that our first couple of years, I mean, a couple of years, but like I think that we definitely were kind of biased in our thinking the first while, like with a vision of what we thought we wanted to make, and should have probably been listening a bit more early and kind of pivoting faster. So I think that's probably a generally applicable piece of advice, just to don't be afraid to adapt what you're doing to feedback that you get.
Cool. And then I also would like to talk a little bit about the social impact of automation. And so people are sometimes a bit anxious, of course, of robotics. They fear that they are losing their jobs. Do you think this is a valid concern? And what are maybe possible solutions to that?
I mean, it's definitely a valid concern. I never want to dismiss anyone's concerns. I think that, from the time they invented the, things to make textiles, which was probably the earliest, forms of automation, there's been people displaced by automation. And I think that, it's never great when someone, loses a job. But I think that there's a lot of opportunities. There's a lot of jobs as well. There's almost no unemployed robot programmers right now. So, it's no consolation as someone who just wants to do welding and not program robots. But I think that the world we live in is going to change, and it's going to change rapidly. And I think that yeah.
And so you think that people could also then move on to something bigger and better?
I mean, I think that yeah, I'm not trying to imply that everyone should just like kind of give up what they're doing, but technology is going to advance, and I think it's you want to do so in a responsible manner. But as a company, we just try to abide by all the regulations that are set out, and yeah.
And so what are maybe some jobs which you already foresee which could become obsolete in the future?
That's a good one. I don't know. I think there'll certainly be things that we look back on. It'll be funny that humans ever did that, but I don't know if I have any unique insight there. But there's a lot of dangerous and unpleasant jobs out there that we could probably automate away.
I guess some people also believe that once we automate everything away, we need some kind of like basic universal income or so. Do you also believe that basic universal income is a good thing and should maybe remedy some of the problems we have within our workforce?
Yeah, I'm certainly not opposed to it. I'm definitely not like a an economics expert, but I mean, if a country is thriving and has the ability to do something like that, I don't see any reason why not to.
Mm-hmm. So you're not like very capitalistic in this point, and
I mean, I would say that I'm not. I don't have any unique. I don't think I have any special thoughts on the topic. I think that it's an interesting one I've heard a lot about, but yeah, I think it's very intriguing.
And maybe let's talk a little bit about how you structure your day. Are there maybe like some daily habits which you do, or something which, I don't know, sets you up for success?
I try to at least stay organized. I definitely try to, because in a startup, you're going to have an endless array of tasks to get done, and so I try to at least take notes on things that I need to get done on a week-to-week basis. And I have kind of a way of prioritize, like kind of making sure I highlight which items are kind of important. So I'll usually start each day and like take a look at what I need to get done that week and what's kind of risen to the top of the priority list. One thing that I definitely try to focus on is making sure people aren't blocked by stuff that I'm responsible for, and so I try to make sure like if people are waiting on product guidance or kind of like technical reviews or something, I definitely try to make sure that people aren't stalled because of stuff that I have to do. So those are usually things that I prioritize. Or if someone else's work is waiting on me, like checking in somehow, whether that's feedback or review or something like that, I try and get that stuff done first.
Yeah, and I guess we are all a bit in this profession of where we are all a bit more desk bound than other people. And so how do you actually combat that? Do you do something against it?
You said desk bound?
Yeah. I mean,
yeah, I mean, I definitely focus better if I've been getting exercise. That's definitely true. I think most people probably benefit from that. And so yeah, after work, I try to get some form of exercise. So it's some running, some stuff outside.
So you have like some goals which you want to achieve?
I'm not super goal oriented when it comes to like hobbies. I used to be, but I found myself getting injured more often. So I try to just do things that I can have fun with, kind of relax.
And so what kind of exercises do you do on a daily basis?
On a daily basis, I'll like go on trail runs. I really enjoy kind of like running around in the hills. I have some friends that I'll work out with. It's always fun to get, especially a lot of people work remotely these days, and it's good to get some human contact, after working hours.
And so what else do you do? Like, so I guess Montana, you could also like do some skiing there or climbing.
There's some really good skiing. We definitely do that. Rock climbing is also a lot of that stuff around as well. I definitely try to take advantage of all the stuff that's around us.
Cool. Well, then thank you for coming by.
Of course.
It was a pleasure for me.
Excited to do it, Andreas. Yeah, happy to chat.
Cool. Yeah, thanks.
Of course.